TD Lambda has some nice theoretical properties that are important to know about. So first of all, the properties, as before, are mostly applicable for linear approximation. So in this case, linear approximation TD Lambda is proven to converge in the on-policy case when we're trying to estimate state values or Q values for a specific policy. If the step size parameter is reduced over time according to the usual conditions, as we saw in the multi-arm bandit topic. Convergence is not to the minimum error weight vector, but to a nearby weight vector that depends on lambda, of course. The error is bounded, the estimation error is bounded by the following term. Here we won't prove it, just know about that. That is, the asymptotic error is no more than this value times the smallest possible error under the current approximation. Of course, linear approximation is usually insufficient in correctly approximating any function, of course, anything beyond the linear function. So the error bound is also a function of the inherent error in our approximation. As lambda approaches 1, the bound approaches the minimum error, the minimum possible error. Full episode return is unbiased. I mean, that makes sense, right? In lambda equals 1, we have a Monte Carlo approach. And in a Monte Carlo approach, we have the error in our approximation will diminish to 0 or to the minimal possible value. And the error is loosest, right? The bound is loosest if we set lambda to equal 0. That is full TD0, or one-step bootstrapping. In practice, however, lambda equal to 1 is often the poorest choice due to training instabilities, right? Because of the high variance in return affiliated with Monte Carlo approaches. What if we would like to extend this approach, TD Lambda, to learn action values, Q values instead of state values for all of the examples that we've seen so far? Actually, this is a straightforward extension, right? It only requires very few changes in order to be extended to action value methods, to Q learning methods. We simply learn an approximation of Q instead of an approximation of the state values, right? And for these cases, we simply use the action value form of the n-step return. So we use Q learning instead of state values. As we've seen previously, we have an n-step Q learning version, definition, and we simply apply them. We've seen that before. For control problems, so far we just saw estimation, or how to estimate a given policy. If we would like to also update the policy and learn a better policy, these are control problems, then usually we prefer doing Q learning, right, which allows us to infer a better policy based on the Q values instead of learning state values, right? And again, as before, it just requires some minor changes, both in the gradient case, in the semi-gradient case, and in our return estimation. And so most of the theoretical guarantees also apply for the Q learning case. That is, TD Lambda will converge on action values for assuming under the conditions that we discussed for the state value case.